the Yantar-directed lasers at our pilots. That Russian action is deeply dangerous.
Recent incidents, such as a Russian reconnaissance ship reportedly blinding a British aircraft with a laser near Scottish waters, underscore the evolving role of laser technology in modern military operations. These events are more than isolated incidents. They signal a strategic shift towards sophisticated optical electronic warfare, or OEW tactics, where laser dazzlers play a pivotal role. Keep your eyes to see how it works. Russian intelligence vessels, the Vishnya class and Yuri Ivanov class ships, are equipped with multiple sensor and weapon systems designed for signal interception, reconnaissance, and electronic warfare operations. For example, the Vishnya class are equipped with sophisticated sensors, including radar systems like the MR-212-201 Palm Frond radar for surface and air surveillance. They also carry communication intercept gear and electronic warfare suites capable of jamming or deceiving enemy sensors. Among these, laser systems, such as dazzlers, are increasingly integrated into their electronic warfare suites. These lasers generally operate within the visible to near-infrared spectrum, capable of emitting directed beams that can temporarily impair or blind optical sensors and human vision. The lasers used are typically of low to moderate power. It ranges from tens to hundreds of milliwatts to achieve non-lethal yet effective optical interference. Some reports indicate that Russian vessels also possess more powerful laser systems capable of causing temporary blindness or disorientation in human targets, including pilots and sensor operators. But how exactly does a concentrated beam of light render advanced sensors and even trained pilots effectively blind in seconds? Laser dazzlers function by emitting intense, focused light beams aimed at sensors, cameras, or human eyes. When directed at optical sensors, they cause saturation or overload of photodetectors, resulting in blindness or reduced image clarity. This is particularly effective against electro-optical systems used for surveillance, navigation, and target acquisition. For pilots and crew inside aircraft, exposure to laser beams can cause visual disruption, momentary blindness, or disorientation, especially if the laser beam hits the cockpit or infrared sensors that assist in navigation and targeting. These effects are typically temporary, but can severely degrade a mission's effectiveness by blinding reconnaissance or combat aircraft during critical phases of operation. By this time, lasers have become indispensable in optical electronic warfare strategies as non-lethal countermeasures to enemy surveillance and targeting systems. They serve multiple roles, blinding optical sensors, disrupting drone operations, and protecting naval assets against visual and infrared reconnaissance. Moreover, integral to their electronic warfare payload are optical laser systems that can influence or disable hostile sensors and aircraft temporarily. These vessels play a key role in gathering signals intelligence, or SIGINT, and conducting offensive and defensive EW operations to support Russian naval and submarine activities around NATO territories. In the context of Russian naval operations, laser dazzlers form part of a layered defense system that can be activated during tense encounters, such as near Scottish waters. The ability to temporarily disable sensors of adversary aircraft or drones offers strategic flexibility without provoking escalation with kinetic weapons. But what gives these beams of light the power to tilt the balance in a standoff, all without firing a single missile? Compared to Western counterparts, Russia has made significant strides in integrating laser systems with their electronic warfare platforms. Russian vessels often combine traditional signal interception, radar, and communications jamming with tactical laser dazzlers, forming a comprehensive optical electronic warfare capability. This integration provides a strategic edge, especially in littoral environments where visual and infrared disruption can prevent adversaries from gaining situational awareness or conducting effective surveillance. Western nations, while developing similar systems, are often reported to lag behind in the deployment of operational battlefield-ready laser dazzlers at sea. British reconnaissance aircraft, such as the Poseidon P-8 RC-135 rivet joint, carry advanced optical and infrared sensors designed for maritime surveillance, reconnaissance, and target identification. These systems include high-resolution electro-optical and infrared sensors cameras, synthetic aperture radar, and infrared targeting sensors. While highly capable, they are vulnerable to laser dazzlers because their sensors rely on photodetectors that can be saturated or overwhelmed by directed laser beams. Moreover, laser exposure poses risks to navigation systems that depend on optical cues, especially in environments with limited GPS signals or contested electromagnetic spectra. The probability of misidentification or navigation errors increases under laser attack, complicating operational planning. Compared to NATO systems, Russia's use of laser dazzlers appears to be more aggressive and integrated, as evidenced by recent incidents involving the targeting of British and possibly American aircraft with laser beams. To understand why these encounters occur and how Russia can achieve such disruptive effects at long range, it becomes essential to look at the very systems enabling this capability. Among the most illustrative examples is the 5P-42 Filin, a purpose-built Russian electro-optic countermeasure that demonstrates how laser interference has evolved from a tactical tool into a fully integrated component of Moscow's naval electronic warfare doctrine. Developed by Roselectronica and documented across multiple technical sources, Filin is designed to impair both human operators and optical sensors simultaneously. Its low-frequency light modulation can disrupt the optic nerve, causing dizziness, disorientation, nausea, or even visual hallucinations. Many media outlets published how Filin works. While it's directed, its beams can suppress night vision devices, infrared rangefinders, anti-tank missile guidance, and other electro-optical systems. This combination of physiological and sensor-level disruption is precisely what allows Russian vessels to challenge NATO reconnaissance aircraft without resorting to kinetic escalation. So, what are your thoughts on this Russian latest improvement on their system? Share it below. Until then, thanks for watching.